Good afternoon, everyone. Let us begin our today's session. Today is week 9. So, today I'll cover week 9 content. So, in this week, Sir has covered, like, he has revised longitudinal stability, which we studied in detail in the performance course. So, longitudinal stability, then sizing and placement of the tail. So, how big should the horizontal tail be? How big should the vertical tail be? And where should they be placed, like how far back should they be placed, okay. And then we studied sizing and sizing of control surfaces. So you know that in an aircraft we have uh, mainly three control surfaces: aileron, elevator, and rudder. So where so how big should these control surfaces be, okay. uh, so we covered that, and then he did a review of the design process. So there was one lecture where he went along the review process, that how you arrive at all these numbers for a aircraft. So first I will cover static longitudinal stability. So here static stability means that the initial tendency of the aircraft to return to its equilibrium, which means that we'll just cover this. Basically, like if the aircraft pitches up like this, then we want it to have a restoring moment which will bring it back down. So we want it to have a restoring moment which will bring it back down. So if the aircraft is pitching up like this, so we just want it to have a restoring moment. Now this is in contrast with dynamic stability. Dynamic stability will consider that how fast the aircraft comes down, or how much long does it take to settle down, okay. Because see, the if the aircraft has pitched up like this and there is a restoring force, the restoring force may not uh, bring it back over here. It might overshoot also, so the aircraft may oscillate about this line, okay. It may oscillate about this line. So how long will it take the oscillations to die down, and all those things are covered in dynamic stability. In static stability, we just study that whether the aircraft has any tendency to return to its original position or not. Okay, so you will see here that this is a positive angle of attack. Okay, so when the aircraft is at a positive angle of attack, we want it to return back to its original position. So this means that the dcm by d alpha should be less than 0, which means that if alpha increases, there should be a restoring moment. So there should be a restoring moment which brings it back to its original line. So now let us see that what are the contributions, like when the aircraft is flying, what are the contributions to its moment, longitudinal moment. So the moment is taken about the CG of the aircraft. So this is the CG, okay. So the forces acting along in this plane are the thrust, then you have the lift, okay. Then you have the lift which acts vertically upwards. You also have the weight of the aircraft. The weight of the aircraft acts along the CG, and the lift of the wing, okay, it acts along the aerodynamic center of the wing, okay. And similarly for the tail, you have another lift vector which acts along the aerodynamic center of the tail. Okay, these are the forces. And now what are the moments? The moments are that you have a moment caused by the wing. Okay, and you also have a moment caused by the tail, but it is usually negligible because the tail size is quite less. Now let us see which of these forces contribute to the moment. So the weight does not contribute anything because it passes through the CG. Okay. Similarly, the thrust vector, okay, the thrust vector usually passes through the CG, so the thrust also has no contribution. However, if the engine is offset from the CG line, so if the engine is placed vertically upward or downward, okay, let us say that the engine was placed up on the tail like this, okay, then the engine may contribute to the thrust vector may contribute to the moment also. Okay. So otherwise, the lift vector, the wing lift, the tail lift, and the uh, moment caused by the wing, these are the primary contributions. So using basic physics, you can uh, write the moment caused by each of these components. So if you consider the moment, so that it will be so first we have the lift, okay, the wing lift, and acts uh, this acts along this distance between aerodynamic center of wing and CG. So you have x bar, no, x AC wing. Um, so and see, this is also a positive moment. So we have x AC wing minus x CG. Okay, so this is the moment due to the wing. Okay, then you have the moment due to the tail, which is minus LT plus you have the moment caused by the uh, wing. Okay, so the moment caused by the wing, so you have MAC. Okay, so these are the basic components. Okay, now over here by LW I mean lift caused due to wing, and LT is lift caused due to tail. Now usually the uh, wing itself, it is not a stable configuration. Okay, so usually we require the horizontal tail to make the aircraft stable. Now you can see that what are the primary factors which influence the stability introduced by the tail. So they are the lift caused due to the tail and the momentum, so the distance between the CG and the tail aerodynamic center. So this distance and the lift caused by the tail. So these are the primary factors which influence the stability. So this is a graph of Cm versus alpha. Acha, in this equation that I wrote, so this equation here, the m does not represent the moment coefficient. Here m talks about the absolute moment. So like including all the dynamic pressure and all. Okay, so this is the absolute moment. But usually we talk about the moment coefficient because you know that the absolute moment will depend on the size of the wing and the velocity you are flying, all these things. So it is better to talk in terms of the moment coefficient. So here we plot the moment coefficient versus the angle of attack, and as I wrote over here, we require this kind of a slope for the aircraft to be stable. Okay, so the graph should have a negative slope and it should have a positive x-intercept. Okay, so this is the x-axis, right? And the graph should intercept the x-axis at a positive value. Because then what will happen is that this alpha e, this will be the equilibrium angle of attack. So when the aircraft will be flying at alpha e, there will be no moment. Okay, and if it is not flying at alpha e, then the moments will cause it to return back to alpha e. Okay, and a positive alpha e means that the aircraft will be positively pitched up and it will be producing more lift. Okay, so these are the necessary conditions, that cm naught must be positive and dcm by d alpha must be negative. Cm naught greater than 0. So this is cm naught. So here you can see it's positive. So here again let us like discuss that what are the contributions to the moment, and these pictures and equations I have taken from John Anderson's Introduction to Flight. So this line over here, it is the zero lift line of the wing and body contributions. So this line represents the aircraft. So over here we have the wing. So this is the wing, and here we have the tail. So and this is the free stream velocity. So you can see that the free stream velocity is coming at an angle of attack alpha. We also have the center of mass over here, and due to downwash, the angle of attack tends to reduce. And then this is the tail over here. So the wing is also producing lift at its aerodynamic center, and the tail is also producing lift, and the tail is also the wing and the tail, they are both kept at a setting angle. Okay, so they are not placed along the line, zero lift line. Usually we have something like this: the wing is placed at a positive setting angle and the tail is placed at a negative setting angle, like this. Okay, so I'll explain why this is the case. So as I said that the moment contribution due to the wing, that will be the CMAC of the wing, and it will be the distance between the it will be the CL, so the lift of the wing. Okay, lift of the wing multiplied with the distance between the AC of the wing and the CG. So this distance, okay, between the AC of the wing and CG multiplied with the lift of the wing, this will give us the CM contribution due to the wing. Now to get the CM contribution due to the tail, we need the lift of the tail multiplied with the distance between the CG and the tail's aerodynamic center, which is denoted by small lt. Okay, so small lt into st into the lift of the tail. But usually the same coefficient is taken with respect to the wing, so we have to divide it by the wing's chord length and the surface area. So what happens is that when we do all this normalization, okay, when we make all these quantities unitless and when we normalize everything, this ratio it comes up in the picture, and this ratio is called the horizontal tail volume ratio. Okay, so this is kind of like a standard number. So uh, even if the aircraft is a little bit like it, there could be many aircrafts of a different class, okay, and there may be some variability between the wing size, tail size, fuselage length, but this volume ratio tends to be a normalized quantity, so it tends to be of the same order. Okay, like you have a, like if you measure these things in absolute terms, then what happens is that for a small aircraft the numbers are going to be small, but for a large aircraft it's going to be large, so it will be difficult to compare and uh, create an intuition about it. But these ratios, these normalized ratios, they are easy to understand. So the moment caused by the tail is negative of the volume ratio into the lift coefficient. So as I discussed in the previous slide, the wing contribution to the tail is minus of the lift of the tail in and the distance between the tail and the CG. So that is here, and then the lift contribution to the tail requires the ST and CLT. So these ratios come up in the picture. Okay, uh, this is the vertical tail volume ratio, and this is the horizontal tail volume ratio. So the horizontal tail volume ratio talks about the horizontal tail, and the vertical tail ratio talks about the vertical tail. And one more thing we'll see is that the horizontal tail ratio is normalized with the chord length of the wing, whereas the vertical tail ratio is normalized with the wingspan. So this is an important distinction. Now I will talk about that how can you, so these are the necessary conditions, right? So how can you ensure that these conditions are satisfied? So first, if I come to the wing, so usually a cambered aerofoil is used in modern aircrafts because the cambered aerofoil uh, it tends to produce more lift than a normal one. Okay, no symmetric one. But a cambered aerofoil will have a quite high, negative CMAC. Okay, the aerofoil itself it produces a quite high negative CMAC. So we need to counter that a little bit. So what we do is we place the AC of the wing a little bit ahead of the CG. So if this is the CG, the AC of the wing is placed a little bit ahead of the CG. Then what happens is that the lift, the lift will act the AC of the wing, right? So this lift will then produce a negative, no, sorry, positive moment. It will produce a positive moment, which will counter the CMAC wing contribution a little bit. So it will reduce it by a little bit. Also, one more thing that we studied in the wing placement chapter, that the wings are usually placed at a small setting angle. Okay, they may be placed at a setting angle of 2 to 3 degrees, so that during cruise the drag is minimized. Okay, now we see that uh, how is the tail placed. So the tail is placed behind the aircraft. Okay, and the tail automatically, okay, the tail automatically satisfies this condition that dcm by d alpha is going to be negative. Okay, uh, by using like physics, like simple physics as I discussed here. So see over here, this is the contribution to the tail. Now the lift produced by the tail will be positive. and this distance is also positive. So the lift is going to be negative. I mean the moment is going to be negative. So the tail automatically satisfies the second condition, that is dCm by d alpha must be negative. But how can we uh, ensure the first condition? So for that what we do is we place the tail at a negative setting angle. So because of this the hmm, because of this the lift produced by the tail is slightly negative, okay, and around the CG. So this is the AC tail. So this one I'm talking of, this figure I'm talking about at alpha equal to 0, okay. So at alpha equal to 0, how can we ensure that Cm naught is positive? So for that purpose, as I said, that we first place the uh, leave aerodynamic center of wing a little bit ahead of the CG, okay. So that creates a positive moment, and secondly we place the tail at a slightly negative setting angle, which causes a negative lift from the tail, and this negative lift when it acts along the CG, it produces a positive moment. So both of these conditions, they create a positive moment at alpha equal to 0, okay. So that is why the, as I said, that the wing and the tail are usually placed like this. The wing is placed at a positive setting angle, and tail is placed at a negative setting angle. So this is how we satisfy the first condition. And the second condition, that the second condition is dCm by d alpha must be negative. So that is mainly contributed by the tail. Okay, that is mainly contributed by the tail because uh, you can see over here that the wing is destabilizing in nature, okay, because the AC of the wing is placed front of the CG. As the angle of attack increases, the moment is also going to increase, so it is destabilizing in nature, whereas the tail is stabilizing. So the this will ensure that the aircraft returns back to its original position. Okay, so this was the revision of static stability. Now I'm going to discuss that. Now I'm going to discuss about the sizing and placement of the tail. So before we go to the sizing and placement of the tail, it is better to have an idea of the fuselage length. So how long the aircraft is going to be. So this distance, so this is what we are trying to estimate, and for this we are going to use statistical data, and it has been found that this relationship is quite accurate. So the fuselage length is equal to a w naught to the power c, where you know that w naught is the gross takeoff weight, and a and c are constants which we can find from this table. So these constants are different for different classes of aircraft, and it has been found that this relationship is quite accurate, okay. This is very accurate and it can be used as a first estimate. So once we know the fuselage length, we have an idea about how big the wing and the tail are going to be. So now we come to the sizing and location of the tail. So the tail consists of two parts, the horizontal tail and the vertical tail. So for the location, so as a first guess, we assume that the tail is placed at some fixed percentage along the fuselage length. So like say if this is the 0% and this is the 100% of the fuselage length, so we assume that the tail is placed at some fixed percentage, and we can modify this location at in the future stages of the design, okay. But for now we can assume that it is placed at some percentage. So here you can see that for an aircraft with a front-mounted propeller engine, the tail arm is about 60% of the fuselage length. So tail arm means that this distance. Okay, so the between the CG and the aerodynamic center. So this is 60%. Okay, for uh, for an aircraft with engines on the wings, the tail arm is about 50 to 55% of the fuselage length. And for aft-mounted engines, the tail arm is about 45 to 50%, and a sail plane has a tail movement arm about 65%. So you can see that the ratios it range from, like, mainly the ratios range from 50 to 60%. Okay, so this means that if you have an aircraft like this, and this is the CG, and this is the AC of the tail. So this distance is approximately 50 to 60%. 50 to 60% of the fuselage length. And one more thing is that the tail also has the vertical tail, and the vertical tail may or may not be placed. It may or may not be placed at the same location as the horizontal tail. But as a first guess, you can assume that they are both placed at the same location. So the vertical tail and the horizontal tail, they are placed at the same location. So this you can assume as the first iteration. Next, we have to size the tail. So what is going to be the size of the tail? So for this purpose, we can use the tail volume coefficient method. So as I said that these non-dimensionalized and normalized values, they are kind of constant for they are kind of constant between different classes of aircraft. So let us say that we are developing some class of aircraft. We can use statistical data to find out values of CVT and CHT, and we know the rest of the values of the moment of the volume coefficient. So then we can solve and find for the tail surface area. So this ratio, if you invert it, you get SVT equal to CVT B wing S wing divided by LVT, and similarly for SHT. Now we know that, so like, see, first we select the wing characteristics, right? So as you know that the primary purpose of the wing is to lift the aircraft, whereas the primary purpose of the tail is to provide stability and control. The tail is not supposed to lift the aircraft. So usually first the wing is selected, wing parameters are selected. So let us say that you select the wing parameters. Okay, so in this equation, you have these BW and SW numbers. Okay, and LVT is the distance between the CG and the vertical tail, which over here we have assumed to be 50 to 60%, right? So this also we know, and then CVT we can find from statistical data. So we have all of these quantities, and so we can find SVT, the tail surface area. Similarly, we can find the tail surface area for the horizontal tail using a similar equation. Now over here you can see one thing that conventionally the wing area, and the tail area, it is measured up to the center line. Okay, whereas you can see that if you are working with canards, then the canard does not go up to the center line, and similarly the vertical tail, it also does not go up to the center line. So this is a table of the tail volume coefficients for different classes of aircrafts. So This is the for the horizontal tail and this is for the vertical tail. And remember that the horizontal tail is normalized with the uh, chord length of the wing, whereas the vertical tail is normalized with the wingspan. And you can see that for different classes of aircrafts, these values are different. Now we come to the sizing of control surfaces. So you know that the wings and the tail, they also contain control surfaces, and these control surfaces should be of adequate size so that they can control the aircraft. Okay, like if they're very small, then they will not have much effect on the flying characteristics. Okay, and it will be difficult to control the aircraft. Similarly, if they're very big, then it will take a lot of force to actuate them, and the aircraft may be very sensitive. Okay, so a little bit of stick deflection might cause a huge change uh, in the angle of attack or the side slip angle. Okay, so it is important to size the control surfaces. So for this also we are going to use some statistical data. So first I will cover the elevator and rudders. Okay, so all of these control surfaces, they have some span and they have some chord. So for elevator and rudder, it has been found that 50%, like if this is the rudder, then the rudder's chord is at most 50% of the vertical tail. So if this is the vertical tail chord and this is the rudder's chord, then the rudder chord by 50%. And coming to the span, so the span is about 90%, and this may be the. So this is usually not stretched up to the tip of the wing, because at the tip there are losses and it is not going to be effective, and it might instead cause disturbances, okay, due to the vortices. Um so it is usually kept at 90%. But one thing is that when these control surfaces are deflected, okay, they may produce a aerodynamic force. Okay, so it might require some force to keep the control surfaces at that location. So there is something called control surface balancing, where we try to what we do is either we put the hinge line a little bit uh, over here, like not at the edge, we put it over here, which reduces this control stick force, or we might have a control surface like this. So we might have a control surface like this. Okay, so this is a rudder, and this entire thing, okay, this entire thing, it moves up and down, and it is about this hinge line. The hinge line is over here, and in this location some heavy mass is placed. Okay, in this location some heavy mass is placed, and this mass helps us to balance the control surface such that a lot of force is not required. So it doesn't take a lot of force to actuate this control surface. Okay, so this tip location may be used for this purpose. It is usually not placed, it is not usually used to control the aircraft, but it may be used to balance the control surface. So for rudders this is the case, and it is also the case for elevators. So if this is the wing, if this is the aircraft center line, and these are the horizontal tail, then chord the rudder chord is less than 50%. So if this is the tail chord, then the elevator chord is at most 50%, and the elevator span is at most 90% of the horizontal tail. Now coming to the wing is more complicated because the wing does not only have the aileron, it has various other control surfaces also. So you can see that is why that the aerial aileron span, it varies a lot. It might vary from 50 to up to 90%. So there are some aircraft where the ailerons are just like the elevators. So you might have, if this is the wing, you might have a aileron which goes the entire way. Okay, so 90%. But this is usually not the case. Okay, there are some aircrafts like this, but normally this is not the case. And also you will see that the aileron, it is used to roll the aircraft, right? So the further away the aileron is from the roll axis, the more uh, effective it is going to be. So this area over here, even if the aileron deflects over here, it is not going to produce much torque because it is close to the roll axis, right? The aileron over here, if this deflects, then it is going to cause a lot of torque. So this area, okay, which is near to the center line, it may be used for other purposes instead of a big aileron, and that is usually the case. So for large commercial transport aircraft, you have other things on the wing also. Okay, so the ailerons are usually placed at the edge. Okay, so these help to, like, they are placed farther away from the roll axis so that they can produce more rolling torque. Okay, and near to the wing, like roll axis, you have flaps. So you have flaps over here, and these flaps are used to increase the CL max during takeoff and landing. And it is desirable that the flaps do not produce a lot of torque. So that is why this location is appropriate actually, because since they're close to the center line, they will, even if there is some imbalance, it will not produce a lot of torque. And there are other things also. You may also have spoilers on the wing, okay, like this. So these spoilers are used during landing or during descent to spoil the lift, so that the, like it, when the spoilers are deflected, they reduce the lift of the wing, and this causes the, and they also increase the drag. So this causes the aircraft to fall and decelerate, and it may be used to rapidly bring down the aircraft. Like let us say you're flying at a high altitude and you have to rapidly come down, you can deploy the spoilers. Similarly, uh, when you're coming in from for the landing, after the aircraft touches the runway, the spoilers may be deployed so that the aircraft doesn't bounce back up. Okay, so there is no bouncing phenomena. So the spoilers may be used for this. Another advantage is that the spoilers may also be used for rolling the aircraft in addition to the ailerons. So at high speed, just using ailerons may cause something called adversarial roll. So in this situation, what happens is that the aileron deflection bends the wing, it causes the wing to bend, and this bending of the wing causes a roll which is in the opposite direction than the intended roll. So let us say you want to roll in this axis, but the aileron deflection, it bends the wing in such a way that we get a roll in this direction, opposite direction. So obviously this is not desirable, right? So it has been found that it is better to use both the aileron and the spoilers like together instead of individually. So how will it work is that, see, if, so these are the spoilers. So if you deploy the spoiler on this side only, okay, then the lift on this side is going to be reduced. So the lift on the right side is going to be less, whereas the lift on the left side is going to be more. So it will produce this kind of a rolling torque. So finally, the aileron span can vary from 50 to 90%. There is a huge variation, but for large commercial transport aircraft, it is on the order of 50%. Okay, and it is placed near the tips, and the aileron chord is 20 to 30%. So this distance is 20 to 30%. Okay, now I'm going to discuss some exercises. This is the first question. Okay, so here the question asks that for static stability level, slope of CM versus CL curve, it is minus 0.15, and the pitching moment coefficient at zero lift is 0.09. Determine the trim lift coefficient. So we can draw the CM versus CL graph. So note one thing here that in the PPT I've discussed CM versus alpha, but the graph can also be drawn for CM versus CL. And in this question, the CM versus CL graph has been asked. Okay. And further it says that the slope is minus 0.15. Okay. And then the pitching moment coefficient at zero lift. So zero lift means that CL is zero. So this quantity is 0.09, and we have to determine the trim lift coefficient. So the trim lift coefficient is the lift coefficient at where the CM is 0. Moment coefficient is 0. So moment coefficient is 0 along this line, right? So over here, so what is this value basically? What is this value that we have to find? So we know the equation. The equation is going to be Cm equal to Cm naught plus uh, Okay, so this is going to be the equation that Cm equal to Cm naught plus dCm by dCl into Cl. So at trim this Cm is 0 and Cm naught is 0.09. dCm by dCl is minus zero point 0.5 and this Cl is the trim Cl. So I'm writing Cl equilibrium. So okay, so if we solve this, we get CLE equal to 0.09 by 0.15 and this comes out to 0.6. So the answer is the third option, which is 0.6. Okay, now moving on. This is the second question. Okay, so in this question, it asks that CM versus CL curve, it has a slope of minus zero point 0.5, minus 0.15, and the pitching moment coefficient at zero lift is equal to 0.09, and the center of gravity of the aircraft is located at uh, zero point 0.3, and the stick fixed neutral point, like we have to find out the location. So for this we will use one formula, which is dCm by d alpha. dCm by d alpha is equal to minus static margin. So here static margin is equal to minus xnp minus xcg. So we know these values, and by solving we can find xnp. So this value is minus 0.15. So this is equal to minus x bar np minus x bar cg. X bar cg is given as 0.3. So 0.15 is equal to x bar np minus 0.3. So therefore x bar np, this will be 0.45. So this is the answer. Now moving on. So this is the third question. Okay, so in this question, the question talks about the uh, like it gives us the moment contribution due to the tail and the wing. Okay, so with respect to alpha, so how does the moment contributed by the tail vary with angle of attack of the aircraft, and similarly how does the moment contributed by the wing vary with the angle of attack alpha? So it gives us both these contributions, and we have to tell that whether the combination is stable or unstable. So over here you can see that the wing contribution is unstable. You can see that cm naught, okay, cm naught is negative. Okay, so let me again draw the graph. So cm naught should be greater than 0, and dcm by d alpha should be less than 0, right? So if I write the wing contribution, this is 0.016, 0.00183 alpha. Contribution due to the tail is 0.16 minus 0.0183 alpha. So you can see that if you consider the wing contribution, then the cm naught is negative and the uh, cm alpha is positive. So it is violating both these conditions. Okay, for the wing. So the wing is unstable. Now let us talk about the tail. So for the tail, you can see that the cm naught is positive and the cm alpha is negative. So the tail satisfies both of these conditions. Now we can find the total contribution. Okay, so the total contribution of the wing and the tail on the aircraft. So it will be the summation of these two. So the total then the total will be, let me calculate, this is 0.144. So this is the net contribution due to the wing and the tail. So you can see that the in this net contribution the Cm naught is positive and the Cm alpha is negative. So it satisfies both of these conditions. So the aircraft is going to be longitudinally stable. Okay. And even if you did not calculate the net moment, if you look over here that the tail has a higher effect, it has a higher effect on the moment than the wing. So the tail is approximately has one order of magnitude more effect than the wing. So if the tail is stable, then it makes the aircraft stable. Moving on, so this is the next question. So this question is similar to the previous question. So here the moment contribution due to the tail has been given like this, and the wing contribution has not been provided. Instead, it has been told that the wing alone contribution is unstable longitudinally. So let us again like, investigate. So we know that Cm naught is greater than 0, like it should be, Cm naught should be greater than 0 and Cm alpha should be less than 0. So, and we also know that the wing contribution is unstable. Now the tail contribution is minus 0.16 plus 0.0183 alpha. So you can see that the Cm naught here is less than 0 and the Cm alpha is greater than 0. So both the conditions are not satisfied. And we also know that the wing alone contribution is unstable. So like there is nothing stable about this aircraft. The wing is unstable and the tail is also unstable. So the overall the aircraft is going to be unstable. So here the answer is that the aircraft is longitudinally unstable. This is the next question. So here, like, let us remember what is stick force gradient. So stick force gradient is a measure of, like, it is a feedback mechanism that if your aircraft, so it is a gradient between the stick force and the velocity, and it has been so the stick force gradient should be positive when the airspeed is lower than the uh, trim speed, and it should be negative if the airspeed is higher. So this is a kind of feedback mechanism by which the pilot can understand whether he or she is above or below the uh, aircraft flying speed. And this is mainly dependent on the properties of the control surface rather than the uh, aircraft moments. So stick force gradient is mainly a function of the hinge moment. So it is not a function of this aircraft moments, but it is a function of the hinge moment, and the hinge moment is the torque acting on the hinge of a control surface. So if I consider the aircraft elevator like this, then the elevator has a hinge like this. So the moment along this elevator hinge, that is the hinge moment, and the stick force gradient, it depends on this hinge moment. Okay, everyone. So thanks for attending. So that is it for today's session.